So it is visible.
Yes, sir. It is visible.
Okay, thank you. So the title of my talk is Modular Properties of the Balancing Sequence and their Applications. And the outline of my presentation is to introduce the balancing sequence, and after that we'll discuss about why actually the researchers are interested in these sequences and why should be, and we'll talk about some fascinating properties of this sequence. And after that we'll define the modular representation of balancing sequence, that is a period, rank, and order of the sequence. And after that we'll talk about the balancing non-Weyfridge primes, and we'll stated few results about these primes. And after that, since there are many applications of this sequence, we'll concentrate in one sequence, one application, that how this balancing sequence is used to do the image scrambling, and that a new transformation is defined that is called balancing QB matrix transformation. And after that, few remarks and references. So in the year 1999, Behra and Panda, they introduced a balancing, a natural number, that is n, which is nothing but a solution of a simple Diophantine equation, that is 1 plus 2 up to n minus 1, which is equals to n plus 1 up to n plus r. So the middle number, that is n, which is omitted here, basically which balanced both the sides, the left hand side and right hand side, and they called this n is a balancing number. So basically this n, the balancing number, is proposed by the Finkelstein in 1965 as a house problem. And what is the house problem? That suppose I live on a street whose houses are numbered in order 1, 2, 3 up to n minus 1 up to n. So the houses at the ends of the street are numbered 1 and n. So my own house number is m, and of course m is lies in between 0 to n. So one day I add up the house numbers of all the houses to the left of my house, and then I do the same for all the houses to the right of my house. So I find that the sums are same. So how can we find m and n? So basically we are interested in the the balancing numbers. Basically the solution of this problem is balancing number. Like if you take an example, suppose I'm staying in the number 6. So if I add the left hand side, the house numbers, that is 1 plus 2 plus 3 plus 4 up to 5, that is 15. Then in the right hand side, 7 plus 8, the two house numbers, that is 50. So basically the 6 is the solution and 6 is the balancing number. Similarly, the second balancing number, we can say that 35, and similarly it is the next one is 204. And this sequence it goes like that, like after 204, 1189, 6930. And how one can test that a number is a balancing number? So that we know that a natural number n is a balancing number, that if and only if 8n square plus 1 is a perfect square. So here if we put n is equals to 6, then we can see that 8 into 6 square plus 1 is 17 square. So we consider that 6 is a balancing number. But we also observe that 8 into 1 square plus 1 is also a square. But as per the equation, Diophantine equation, or as per the solution of 1 is not a solution. But here 1 satisfies the condition 8n square plus 1 is a perfect square. Therefore, we considering that 1 is the first balancing number, and 6 is the second, and so on. So basically, these numbers follow a recurrence sequence, linear recurrence sequence, and that linear recurrence is that bn plus 1 is equals to 6bn minus bn minus 1. With initial condition, we are considering as the b0 is 0 and b1 is 1. And this number sequence, yes?
Sir, just in the previous slide, previous to previous one, you said 6, this one. 6, 35 and 204, they are the balancing numbers. ये तो समझ में आ गया, but what are the balancers? Like how you defined balancers to 14 and 84 of these balancing numbers?
Okay, so basically in the definition, we are saying in the right hand side that R is the balancer, means here in this equation 1 plus 2 up to n minus 1 is equals to n plus 1 up to n plus R. So R is called the balancer, since I'm not emphasis in R because because my application based on balancing sequence. So here so you can see that in the right hand side it is n, the 7 is the first and the 8 is second. Basically there are two terms in the right hand side in the first equation. So therefore I am saying that 2 is my balancer. Similarly in the
6
second
plus 1
equation,
and then 6 plus 2, a value of R will be 2 then.
yes.
Okay.
So
Thank
that
you,
is okay. So one can check like that. If the condition 8n square plus 1 satisfied, then it's a perfect square. And the non-recurrence relation, the balancing sequence satisfy is bn square minus bn plus 1 into bn minus 1 equals to 1. And sometimes it's called as the Cassini formula of this sequence. So if b is a balancing number, then the square of these numbers are triangular numbers. And as we said, that 8b square plus 1 is a perfect square. And one interesting that if we do the square root of 8b square plus 1, it generates a new sequence, and that sequence is called Lucas balancing sequence, which satisfy the same recurrence relation as balancing number, that is Cn plus 1 is equals to 6Cn minus Cn minus 1. With the initial, here the initial condition is different, with C0 1 and C1 is equals to 3. Now, the binary formulas of these numbers are that Bn is this lambda 1 to the power n minus lambda 2 to the power n by lambda 1 minus lambda 2, and Cn is the respectively. And here the lambda 1 and lambda 2 are the roots of the characteristic equation, and which values are 3 plus 2 root 2 and 3 minus 2 root 2. So a natural questions arises that why actually the researchers are interested in this sequence, because all of us know the Fibonacci sequence. It's a very famous sequence and very well known, and it has numerous application in every field wherever we can find. So why one can interested in this sequence? So like if basically all of us study the a natural sequence, everyone is studying about the natural sequence. So basically this sequence, balancing sequence, follow the properties of natural numbers. Like the first property is like De Moivre's theorem. Okay, it follows that Cm is the Lucas balancing number. So Cm plus root 8 Bm whole to the power n, that is your Cmn plus root 8 Bmn. Then the next property is like trigonometric properties. It follows like sin x plus minus y. Okay, sin x into cos y plus minus cos x into sin y. So the similar type of property. And the third property is the divisibility properties. So these are the few properties are there, and some few important properties like this one, that why it is different from the Fibonacci numbers. Because the balancing number here, these properties, like the arithmetic properties, that we know that a plus b into a minus b is a square minus b square. So you can see that the balancing sequence Bm plus n into Bm minus n is satisfying Bm square minus Bn square. But the Fibonacci numbers is not satisfying the similar properties. So which is not so natural like balancing numbers. And if you talk about one more properties, that this balancing numbers behave like also natural numbers. Like if you we know that if you do the sum of n odd numbers like 1 plus 3 up to 2n minus 1, that is n square. So here, like if you do the same thing with balancing sequence, so b1 plus b3 up to b2n minus 1, that gives you bn square. And like similarly, if you add the even numbers 2 plus 4 up to 2n, like that is your n into n plus 1. So here similarly, the balancing sequence satisfied. So basically these properties, these natural properties are not satisfied by the Fibonacci sequence, but though balancing sequence is satisfied. So these are the some basic properties since the researchers are interested. And now we'll talk about some modular properties. That now we'll define the period modulo m. Okay, so period modulo m of the balancing sequence, that is denoted by pi of m. That is the how it denotes or how it is defined, that it is the smallest positive integer t for which bt congruents to 0 and bt plus 1 congruents to 1 modulo m. So to understand, we'll go through a simple example. Like our balancing sequence is like 0, 1, 6, 35, 204, 1189, 6930, and so on. So if you do the balancing sequence with modulo m, so m is a positive integer, so m is 5. So let m equals to 5, then it is 0 modulo 5, and 6 congruents to 1 modulo 5, 204 congruents to 4 modulo 5, again 6930 congruents to 0 modulo 5. Okay, sorry, b0, b1, b2, b3, like that. So it is, so basically we are interested in the residue. So what are the residue we have got? That is like 0, 1, 1, 0, 4, 4, and again we got 0, 1. So the definition says that whenever the 0 and 1 coming consecutively, smallest after the first 0, 1, when it will come consecutively, we have to stop here. And like when 0 and 1 coming consecutively here, we have stop here, and the period is 0, 1, 1, 0, 4, 4. So the that means the balancing sequence period modulo 5 is 6. Similarly, it is for one can find for for all m. So this is how the period is defined by the Panda and Raut in 2014. I think, yeah, in 2014, and they have defined the period, and they have studied few properties of this period of the balancing sequence modulo n. That if m divides n, then pi m divides pi n. If m divides bn, then pi of m divides 2n. So few interesting properties they have studied related to the period of the balancing sequence modulo n. Then we in our work we have defined, we extend the we have just studied more details about this periodicity, and we have defined the rank of balancing sequence modulo m, and we have denoted it as alpha m. And how it is defined, that is the smallest positive integer k such that m divides bk. And we also defined the order of the balancing sequence modulo m, that is om, and it is defined by the order of the b alpha m plus 1 modulo n. So like if you take the same example, that balancing sequence modulo 5, then this is the residues. There's 0, 1, 1, 0, 4, 4, 0, 1, 1. So as per the definition of the rank, it says that whenever the 5 divides the balancing sequence, that means when the residue is 0. So whenever we will get the first 0, that is the rank. So alpha of 5, you can see that 0, 1, 1. After that, at the fourth we got the 0. So that means the 0, 1, 1 are the, so there are 3 terms before 0. So we can say that 3 is the rank. And what is the order? How it is defined? The order is B alpha m plus 1. So what is the B alpha m plus 1? So alpha 5 is, we have got 3. So B 3 plus 4. So B4. So B4 is what? After 0 it is 4. So we have to find the order of 4 modulo 5. So we know the definition of order. Okay, that is the in general. So that means 4 is not congruent to 1 modulo 5. So just raise the power of 4. So 4 square congruent to 1 modulo 5. So here it is the order is 1. So residue is 1. So here 4 square. So its order is 2. So basically order of 5 is 2. So like this we have defined the rank and order in our study. Okay, and we established an this interesting result related to the period, rank, and order. And this result says that the period of the balancing sequence modulo m is equals to the multiplication of rank and order of the modulo m. So basically, rank and order is equals to your period. So that is established in 2016. And also in the same work, we have also established few properties related to rank and order. Okay, so one of the interesting properties that the order is either 1 or 2. Okay, that your first 0, I mean the order is 1 or 2 means your 0 may be either 1 or 2 0 you can find after the in between the period. Okay, so these are the results, some results based on the rank. So that's what I talk about a little bit about the modulo m, balancing sequence modulo m, and about the period, rank, and order. So let us discuss little about Wefridge primes, and then we again come to the period. So this Wefridge primes. So what is Wefridge prime? That an odd prime p is called Wefridge prime if 2 to the power p minus 1 is congruent to 1 modulo p square. So any odd prime p satisfy this congruence, then we can say that prime is a Wefridge prime. And those prime which not satisfy this congruence, it's called non-Wefridge primes. Okay, so Wefridge prime and non-Wefridge prime. And Wefridge, the mathematician, proved that if an odd prime p is non-Wefridge prime, then there are no integer solutions to the Fermat equation x to the power p plus y to the power p equals to z to the power p when p does not divide x by z. I mean x into y into z. So basically, Wefridge established a relation between the non-Wefridge primes with the Fermat's last equation. Okay, so and so this interesting relation also we got it in the balancing Wefridge prime, non-Wefridge prime also. And till date, there are only two Wefridge primes we know, that is 1093 and 3511. And it is a still open problem that are there infinitely many Wefridge primes. So it is a still open problem. And basically the proof is based upon the ABC conjecture. So it is not solved till yet. Okay. So this is the we talk about the Wefridge prime, and the Panda and Routh conjectured that there are three numbers, that is 13, 31, and 1546463 are the only three primes satisfying the condition that period modulo p is equals to period modulo p square, and that is analogous to the congruence this b of p 8 by p congruence 0 modulo p square. And they also. And later works, Routh called these primes, this 13, 31, and 1, 5, 4, 6, 4, 6, 3, these primes, they call these primes are balancing, Wirich primes. And those primes which are not satisfy this condition or this congruence, then it is called balancing non-Wirich primes. So it's also an open problem that there are only 3 primes, or one can prove that there are infinitely many primes. So basically it's a conjecture. So the conjecture is still till yet not solved. So Routh just gives the name of this is balancing Wirich prime, and those who are not satisfying this congruence is called balancing non-Wirich primes. And basically Routh give the statement, they study in details about these primes. Basically, Routh interested in balancing non-Wirich primes, those primes which are not satisfy this congruence. And they established few results about balancing non-Wirich primes. And for that, basically this ABC conjecture is required. So I'm just recall here that basically this is the statement of ABC conjecture for integers, that let ABC be mutually co-prime positive integers with A plus B equals to C, and let epsilon is greater than 0, then there is a constant C such that maximum of absolute value of ABC is less than or equals to the C into radical of ABC to the power 1 plus epsilon. And basically the work is depend upon the ABC conjecture over the algebraic number field. So the ABC conjecture of the algebraic number field is given by the mathematician Gowry in 2008, and basically the proof is based upon the conjecture of ABC conjecture of algebraic number field. So the ABC conjecture is defined over the number field is this one, that for any delta greater than 0, we have this height of ABC is less than or equals to radical of ABC to the power 1 plus delta. And using this conjecture, Routh established this result that there are infinitely many balancing non-Wirich primes are there. So he assuming that ABC conjecture is for the number field Q root 2 is true, and he proved that there are infinitely many balancing non-Wirich prime are there in arithmetic progression. And after established this result that there are infinitely many primes, he also proved in the same paper, he gave an lower bound of these primes, and he gave the lower bound is that the number of primes P which satisfy this congruence property is log x by log x. So these are the important results he established in his paper in 2016. And after that, we have improved its lower bound. Its lower bound is given as log x by log x. So we use the Hardy and Wright, using this identity or this properties or using this result, we have improved the lower bound, and we have from this log x to log x by log x to log x by log x into log x to the power m. That's in our work. So after that, this lower bound is improved in 2019, and recently in a recent paper, Anitha, Fatima, and Bijan has increased the lower bound to log x. So this is the recent upper bound. So this is the I just want to discuss about the balancing non-Weyfridge primes. And till now, its lower bound is improved up to log x. So the remarks is that since there are, that Routh has proved that there are infinitely many balancing non-Weyfridge primes are there. So one can improve the lower bound of this balancing non-Weyfridge primes. So the interested researchers can encourage to do that. So this is about the modular representation of balancing sequence. And since there are the application of balancing sequence in different fields, okay, like in image scrambling, in coding theory, so there are many applications of this sequence. So in my presentation, I just want to discuss about one application, that is about how we are using this balancing sequence to image scrambling. So for that, I am introduced the balancing matrix that is defined by the Ray in 2012, that the 2 by 2 balancing matrix, which is denoted as QB, is 6 minus 1 1 0, where basically the elements of the matrix are the first three balancing numbers 0 1 and 6. And these matrices also follow the same recurrence relation as balancing sequence, that is your QBN is equals to 6 QB1 to the power n minus QB2 to the power n, where QBN is your Bn plus 1 minus Bn, Bn minus Bn minus 1. So basically the QB6 minus 1 1 0 is a particular matrix, and it's the power of QB to the power n matrix is Bn plus 1 minus Bn, Bn minus Bn minus 1. So based upon this matrix, what we do, we extend this matrix. So like it's a 2 by 2 matrix is defined by Ray. So we extend this 2 by 2 matrix to 3 by 3 matrix, 4 by 4 matrix, up to n by n matrix one can able to extend. And we do that without loss of generality of the Cassini formula, Bn square minus Bn plus 1 into Bn minus 1 equals to 1. So the 3 by 3 matrix, we have just extended as 0 minus 1 0, 0 0 minus 1, 1 6 0. Basically the matrices are basically first three balancing numbers. So basically QB3, QB4 and so on, one can able to extend. Then before we just a little bit overview before we talk about our work. So image scrambling is a useful approach to secure the image data security by crawling the image into an indiscernible appearance. And the first, the Arnold Cat map, or which is a chaotic map from the torus into itself, is widely used for the image encryption. And Arnold has introduced in 1967, and this Arnold transformation is nothing but a mapping from t square to t square, such that x dash y dash is equals to 2111 into xy modulo capital N, where this xy belongs to lies in between 0 to n minus 1. And n is what? N is the size of a digital image. So in this, so here the matrix 2111 Arnold has considered. Okay, and Arnold also showed that it can be effectively used in the image scrambling because of its periodicity. So after that, other researchers like Dong Zhu and Bing and Zhou et al., they also defined many other transformation like Fibonacci transformations, and also by other integer sequence they have defined. Okay? And they have studied about the scrambling image of scrambling of the images. And In 2012, Mishra et al. Proposed a new spatial domain image scrambling method which is based on Fibonacci and Lucas series. So this study is done by Mishra et al. Based on the new spatial domain, and this method has wide application in various spatial domain image processing techniques of data hiding and secret communications. And their conclusion was important because they have claimed that the transforms with higher periodicity may reduce the level of security as those can be decrypted by the other maps, even if the exact map is not known. So their conclusion is that if the the level of security is depend upon the periodicity. So if the periodicity is more, then the level of security is less. And for that, we have defined the balancing QB matrix transformation by this operation, that x1 dash x2 dash up to xp dash. Basically, this is the new image. You can say this is congruent to QBP. QBP is the balancing matrix into x1 x2 up to xp modulo n. x1 x2 xp is our original image, and the x1 dash x2 dash is the new output, the new first iteration image that one can see. So as the Mishra et al. Whatever they claimed, that if the periodicity of the image is higher, then it's the level of security is less. So for that one, here we have got we have find for the balancing QB matrix, QB transformation. This is the periodicity table for 3-dimensional balancing QB transformation and 4-dimensional balancing QB transformation. And how, I mean, when I am saying the periodicity here, that means that if you use the operation like this transformation to an image, then it will be, a new image will be there. And if you do again the same operation to the new image, then after some times again the original image will become. Okay, so that is the periodicity, that till the same original image will not come. Okay, we have to proceed like that. So basically, the smallest positive integer n, such that the image p can come back after n times transformation. That is the periodicity. And this is the few table of the periodicity. And what we observe that basically, as compared to the whatever the established transformations like Fibonacci transformation, Arnold transformation, Lucas transformation, whatever the already established, the balancing transformation gives the lower periodicity. It's so if it lower periodicity, that means it gives the higher security. So therefore we study this one, and basically our transformation is based on the phase spaces. So the phase space of a dynamical system is a space in which all possible states of a system are represented, with each possible state corresponding to one unique point in the phase space. So basically, a digital image can be regarded as a matrix, and the position of an element of the matrix is the coordinates of the image pixel, and the element of the matrix is the gray level of the pixel. And our study is also based on this phase space of a dynamic. And what we actually do, suppose the original image is P, okay, and the pixel value is suppose P11, P12 up to P1n, because the image can be regarded as a matrix. So suppose that our original image is P matrix, then the new image is P dash, and A is our balancing QB matrix for n by n matrix, and we are using the operation P dash is equals to A into P modulo T, and that is our operation. And the image coding, how do we do the encoding? So the algorithm is that consider an image. Second step is to balancing transformation is applied on the input image to obtain the temporary image. Third step is if temporary image is the original image, then display the temporary image and its paired. Choose an encoding image whose iteration lies in between original image and its period. Okay, so we have to choose one image from one image from the period, okay, in between the original image and its period, and we have to send it to other side. And how one can decode it, that input encrypted image, that is basically temporary image, we are considered as encrypted image. Then multiply temporary image with inverse balancing matrix. Then take modulo of output image of step 2 with T and take it as temporary image. So continue step 2 and step 3 until the original image reached. So like if you take if you consider an example, like suppose we have considered an original image of size 20 cross 20, and we are implemented in MATLAB. So we have considered the original Lina image, and the first figure 1 is that after the scrambling of 203 times we got the first image, and if you do the or if you apply the balancing transformation 422 times in the original image, we'll get the figure 2. So one can take any one and they can send it to the other side. And so this is the example. That's what we did. And the few remarks about that, what I earlier said, that since Mishra et al. Proved that the transformation with higher periodicity may reduce the level of security, and as those can be decrypted by other maps, even if the exact map is not known. So based on this argument, since balancing transformation has a lower periodicity, the level of security is higher in the image scrambling as compared to the other transformations. So this is just an example of balancing sequence, and other applications are there also in coding theory. And these are few references. Thank you. Thanks.
Yes, I have a query, Dr. Patel.
Yes.
That image encoding and decoding part you had explained at the end, and you had implemented using MATLAB, I think.
Yes.
So what is the experimental configuration actually you have taken? Because image processing actually it requires high-end configuration things. So for image transformation, so what type of experimental configuration you have taken for?
Yeah, actually, sir, we are focused on the mathematical part. We actually our one of the author is from computer science. Basically, we take help from him.
Okay, sir. Okay.
Yes.
Okay, because we are applying deep learning concept for image processing, and we are taking the GPU kind of things. So
yes, I actually just want to give an application of balancing sequence. So
okay, that mathematical part, yeah, you have let me say implemented the mathematical things. Or the okay.
Yes.
Okay, thank you. If any other members have any query. Okay, fine. Now I will. Yeah.
So, okay. Basically, the Cassini formula is given in textbook. Like if you interested in, like there is a book Fibonacci and Lucas sequence and that application by Thomas Cossi. So one can refer that book. Thomas Cossi.
Okay, fine. Thank you. Now I'll request Dr. Abhijit Sutradhar to give the vote of thanks.
Thank you, sir.
From my side also, thank you, Dr. Patel, for agreeing within a short notice to deliver a talk. Thank you.
Thank you. Thank you.